It's really nice to have Professor Luca Carlone joining us today. He's a Leonardo Associate Professor in the Department of Aeroastro at MIT. Leonardo Professor, I like that title. That's just amazing. Yeah, a PI, also a PI at the Laboratory for Information and Decision System at MIT. His research includes the nonlinear estimation, numerical and distributed optimization, probabilistic inference, applied them to the robot perception and vision-based autonomous navigation. He made seminal contributions to the certifiable corrector algorithm for localization and mapping, as well as approaches for visual inertia navigation and distributed mapping. At MIT, he teaches robotics, science and the system. This is an undergraduate, very popular class. And also he created the graduate level course on visual navigation for autonomous vehicle. He's a recipient of many, many awards, includes the Best Paper Award in Robots Vision at ICRA 2020, the NSF Career Award, the Google Daydream Award, the Amazon Research Award, as well as the MIT Aeroastro Vicky Carey-Brock Family Award. So without further ado, let me invite Luca, please.
All right, thank you so much. Let's see if the screen share is working here.
Yeah, it works.
Okay,
well.
can you confirm you hear me? Okay,
yes,
perfect. So thanks for the kind introduction, Jinhua. And also thanks everyone just for jumping in and writing in the chat. It's just fantastic, to be here. I've been following many of the meetings of the Mobility Forum this semester, and it's really a pleasure to discuss with all of you today. So as Jinhua mentioned, I'm Luca Carlone. I'm an associate professor at MIT, and I'm the director of the Spark Lab at MIT. So with this cover slide, let me start just by giving credits to the students and postdocs in my lab who are doing really the heavy lifting behind many of the contributions I'm going to present today. So the plan for today is to kick off the discussion by giving you a quick overview about self-driving vehicles, reviewing the promise and reality of self-driving in 2022. And then I will zoom in on spatial perception, which is a key algorithmic component of self-driving cars. And then I will tell you about our work on increasing the robustness of spatial perception for robots and autonomous vehicles, including our work on certifiable perception algorithms, high-level 3D scene understanding, and perception system monitoring. I'll start by mentioning that while my group is working with a few self-driving car companies, this presentation, of course, is just my own opinion. Okay, so for the last 10 years, we have seen a growing effort in deploying self-driving or automated driving solutions. And it's not uncommon at this point to see self-driving cars on our streets. For instance, if you live in California, you might have seen the Waymo car. If you live in Arizona, you might have seen the GM or Cruise self-driving cars. And of course, everybody will be familiar with the Tesla autopilot. And there are many, many other efforts, as the one that we heard about a couple of weeks ago from Professor Leonard about the ongoing effort at TRI. So a self-driving car or automated vehicle is simply a vehicle that is capable of sensing and understanding the environment and is able to move effectively and safely with little or no human inputs. It is worth remembering that self-driving capabilities are not really a binary feature, but rather constitute a spectrum of capabilities, which are typically quantified, as I'm showing on the right here, by the SAE levels of automation. I will not go through the details of all of them. I'm sure many of you will be familiar with this, but you can think about, for example, level 0 corresponds to no automation. Level 2 corresponds to the case where the car drives, but the human is responsible for monitoring the surroundings and taking over in case of emergency. Level 4, in level 4, automation does everything, but only operates in certain driving conditions. You can see that in the last column, just some driving modes. And in level 5, automation completely replaces the human in all driving conditions. So just to keep these a little bit more grounded, you can think about Tesla's autopilot as currently being classified as a level 2 system, while the other self-driving cars in this picture are classified as targeting level 4 of automation. So just for some context, why do we care about self-driving cars? First of all, self-driving cars carry the promise of saving lives. Currently, we are suffering more than 1.2 million fatalities per year and more than 50 million injuries due to car accidents. And more than 90% of these accidents are due to human errors, including speeding, drunk driving, or distracted driving. Well, self-driving cars simply do not get drunk, and they can be programmed not to get distracted or not to speed. Second, self-driving cars, in particular for high level of automation, have the potential to increase mobility for seniors and people with disabilities and really expand transportation options for underrepresented communities. This is particularly important considering that by 2034, as shown by the statistics I'm showing here on the right, the number of older adults in the United States is expected to outnumber the children under age 18. Finally, self-driving cars have the potential to save money. Americans spent an estimated 6.9 billion hours in traffic delays, that was in 2014, and automated driving has the potential to increase the road network efficiency and simultaneously reduce traffic while enabling a more effective, more productive use of the commute time. In addition to that, automation will have the potential just to reduce the need for parking spaces. And there is, of course, an economic gain just in reducing the number of accidents. So there is a big promise for self-driving. Indeed, currently, there are more than 1,000 self-driving cars being tested or deployed in the United States. You can go on the National Highway Traffic Safety Administration website. That's the NHTSA website. And you can find a map, such as the one I'm showing here on the slide, of where many of the self-driving cars are being deployed, and what is a list of companies, governments, or associations in the United States currently testing self-driving technologies. I'm just giving an example, a non-comprehensive list of companies here on the right. And there are, of course, many, many more. Just to give you a sense of the momentum some of these companies have, Waymo drove 2.3 million miles in 2021 alone, and almost tripled the size of his fleet in 1 year, moving from 249 cars to almost 700 cars. At the same time, the growing deployment is also increasing the number of accidents experienced by self-driving cars. This slide is based on a recent article from Business Insider, which reports that the increasing deployment of self-driving cars in San Francisco has also led to a larger number of collisions and accidents. For instance, Waymo has been experiencing more than a threefold increase in the number of accidents between 2020 and 2021. In particular, here in the table on the left is reporting the number of self-driving car accidents only in California, comparing 2020 with 2021. And the x-axis of the plot is organized by type of accidents, while on the right, we see the same number about number of collisions and accidents, but organized by different companies. So if you aggregate data across multiple companies, we just see that the increasing number of collisions reveals the imperfect state of self-driving and shows that there are still many technical challenges to be solved. Remember that these failures are typically of level 4 systems or below, while currently there is not even a level 5 system. Level 5 is still considered out of reach for the current technology. So today I want to focus on specific technical challenges, a specific technical challenge which is fundamental to self-driving and for robotics in general, which is spatial perception, and tell you about the work we are doing on improving spatial perception. So just to start, what is spatial perception? Spatial perception is about using sensor data to understand the surroundings of the vehicle. Consider, for instance, a car navigating through an intersection. In order to cross the intersection safely, the car will have to detect the boundaries of the traversable space, will have to detect other vehicles and pedestrians, we need to track the speed of other vehicles, and also, of course, detect traffic lights, traffic signs, and so on. And these are all spatial perception problems. Essentially, it's about understanding the environment and understand things that live in the space around the car. Okay, sorry. So in other words, spatial perception is really about using sensor data to build an internal model of the external world from sensor data to this internal model. And perception is a crucial capability for self-driving cars, but is also very important to other applications of robotics that personally also care a lot about, including domestic robotics, factory automation, infrastructure monitoring with drones, and even applications that are not typically associated with robotics, such as augmented reality or virtual reality, are using similar algorithms as the one that we study in spatial perception for robotics. So in recent years, we have really witnessed an impressive progress in perception algorithms. We now have compelling algorithms for simultaneous localization and mapping, or SLAM, as the one I'm showing here on the left. SLAM is essentially about building a 3D map, picturing the geometry of the environment in 3D, and doing so in real time. Moreover, the advances in machine learning have provided effective solutions for object detection and 2D semantic understanding. So in object detection, the algorithm essentially tries to detect bounding boxes of the objects as the one that you see here in yellow, while in 2D semantic segmentation or 2D semantic understanding, the problem is about labeling every pixel in an image with a corresponding semantic category. For example, pixel can be classified as road, belonging to the road, belonging to a pedestrian, belonging to a car, and so on. And again, deep learning techniques are doing just an amazing job at this point at solving these problems. Indeed, the combination of these three technologies has been a true enabler for a number of applications, and of course, for self-driving vehicles, but also for other applications of robotics, such as autonomous drones. At the same time, the broad adoption of this technology, of perception technology, is also revealing fundamental limits of existing algorithms. Many of you have seen this. This is an example from March 2018, where the perception system of a self-driving Uber vehicle failed to detect a pedestrian and provide a timely warning to the backup driver, to the safety driver, resulting in the killing of a woman in Arizona. And unfortunately, there are many examples like this. The one at the top right here is an example for 2018, where the Tesla Model X autopilot misclassified the concrete barrier, the concrete separator on the left of the car, and decided to turn into it. Many of you might also be familiar with the example at the bottom here. Of course, these are stop signs. A neural network in nominal condition will do an excellent job at detecting these stop signs. But if you place carefully these black and white stickers on top of the stop sign, you can mislead a neural network to classify, and use a neural network to classify these as 45 miles per hour speed limit, which is a pretty bad mistake to make at an intersection. So there is plenty to be done to address this kind of failure modes and corner cases. What I want to do in the rest of the presentation is really to jump in on the work we are doing on our side. We are, of course, addressing just a small portion of all these big technical challenges. And I want to give you an overview of the work we are doing towards increasing the robustness of spatial perception for both our robots as well as autonomous vehicles. I will cover certifiable perception algorithms, high-level scene understanding, and perception system monitoring. Of course, that's a lot. So I will literally spend 2 or 3 slides on each contribution, and I will try to keep it high level just to give you a flavor of each type of work. So let me start by discussing our work on certifiable perception algorithms with some focus on 3D object pose estimation. So for those of you who are not familiar with this problem, just to set up the stage, consider the case in which you are given an image, and we have to estimate the pose, which is simply the position and orientation of the object in the image. In this case, we want to estimate the position and orientation of the car given this image. A popular approach to solve this pose estimation problem is to first use a neural network to find a set of the location of specific features in the image. For example, the neural network will localize, the corners of the windshield in the image, the location of the wheels, the headlights, and so on. And then, given an ideal model of the car, one can apply a second stage where we solve an estimation problem that finds the best 3D pose of the car, such that the ideal model projects at the correct location in the image, or in other words, it fits well the features the neural network has extracted. Again, we have a 3D model, an ideal model, and we solve some estimation problem to position it correctly such that it makes sense when projected to the image. So while the one in the previous slide was kind of an idealistic example, an ideal example of the operation of this feature detection and estimation, what happens in reality is that the neural network detections are not perfect. And while the network correctly detects some of the features in the image, the ones that are shown in green, which are called inliers, many other detections are outliers or are misdetections and are the ones that I'm showing in red in the image. Then the problem is that if there are too many outliers, the estimation module might just return an incorrect estimate, as in the example in the figure where the yellow silhouette is where the algorithm, the estimation algorithm, thinks the car is, which of course as humans, we understand as being an incorrect estimate because it does not really match the silhouette of the car. So while many researchers have been focusing on designing better neural networks to reduce the number of outliers, so better neural networks for the feature detection, over the last few years, we have really focused on how to develop better estimation techniques that are able to solve estimation problems in the presence of extreme amount of noise and outliers. this presentation is not super mathematical, but just to make the discussion a bit more grounded. The estimation module typically involves solving an optimization problem that is looking for a variable X. In this case, that's the pose of the car we are looking for, and is going to look for the best fit for the variable X, which is producing the best fit for the measurements YI, which are the features that the neural network has detected. So this optimization problem is a challenging one, again, because of the fact that the measurements are quite noisy. Some of them might be outliers. And the optimization problem also suffers from a number of technical challenges, such as non-convexity. So therefore, with this line of work, we really address the question, can we develop estimation algorithms that are robust to a large number of outliers and also provide some optimality guarantees? So this has led to the development of what we call the certifiable perception toolbox, which is a collection of algorithms and implementations for these difficult estimation problems. The toolbox includes graph theoretic algorithms that find large set of compatible measurements and prune out gross outliers, as well as optimization techniques such as graduated non-convexity that mitigates the non-convexity of the problem and allows finding better solutions. Finally, we also propose more fundamental contributions, such as the use of novel semi-definite relaxations to check the correctness and optimality of an estimate, such as we can essentially distinguish correct estimates from incorrect ones. In particular, the moment relaxation is what allows us to obtain the first certifiable algorithms, which are algorithms that compute a solution and either certify that the solution is optimal or detect failures otherwise. So for some problems, we also provide what we call an estimation contract, which is essentially a technical result that guarantees that if the number of outliers is sufficiently small, we can always recover with these algorithms, we can always recover the correct pose of the object. So of course, this is not a mathematical presentation, but I just want to take one slide about to give an intuition about the technical approaches we use. So you can think that the optimization problem we're trying to solve is essentially searching for the lowest point of a function, the minimum of a function. Such function is non-convex, which mathematically means that the function has multiple valleys, as the one that you see here. There is a big one, but also a number of small valleys. And if an algorithm is able to find the lowest valley, it will produce a good estimate for the location of the car. If instead the algorithm is stuck in other valleys, it returns a poor estimate of the solution of the position of the car. Then essentially what our approaches are doing, they're approximating the non-convex function, which is difficult to optimize, with a nicer one, with a convex one that has a single valley. And then they're gradually tracing back the solution from the convex approximation to the original non-convex function. Of course, here I'm visualizing just a very toy, like, to the example, just for the sake of visualization. The problems that we typically solve are much more complicated than that, and they are high dimensional. And similar for the case of the semi-definite relaxations, again, if you don't care too much about the mathematics, you can skip this. But the idea is that we essentially map the original problem, which is again non-convex, to a higher dimensional space where the problem becomes easier to solve. Let me jump to the practical implications of this work. So the practical impact of this work has been really the design of a new set of algorithms that are hard to break and are robust to a large number of outliers. For instance, we have new techniques for pose estimation in point clouds that are robust to 95% of outliers. We have techniques for pose estimation from images that are able to tolerate 70% outliers. And moreover, these approaches also apply to very different estimation problems, such as the one arising from robot localization and mapping, where we've also shown that these algorithms enable extreme robustness to outliers. And maybe the important bit here is that many of these techniques at this point are released in standard libraries, including GTSEM, which is a popular library for robot perception, as well as MATLAB, which I'm sure all of you will be familiar with. Okay, moving to the second topic, it's worth mentioning that as we make progress towards solving these optimization problems for pose estimation, we just realized that detecting objects is much more than optimization and geometry, it's much more than just mathematics. And we realized the importance of high-level 3D scene understanding for robust spatial perception. So let me give you an example of what I'm talking about here. So if I present this slide to you and I ask you to detect the car in this image, I'm sure you will have no troubles doing so. Everybody will see the car. However, if I show you the full image from which I cropped the shape of the car, you can stare at this image for a few seconds, right? And after a few seconds, you can realize that actually in this image, there is no car. There is just a white van, and the car is actually painted on the van. To draw this conclusion, probably your mental process was something like the following. You started by detecting the ground plane. You then detected the presence of the car. You detected the presence of the van. And then you reasoned on the fact that the car and the van cannot be physically on top of each other, and therefore the car must be painted on the van. In other words, what I'm saying is that to interpret the image, you did not detect objects in isolation, but you rather reasoned over semantics and relation between objects in 3D. Therefore, here, what I'm arguing is that the robustness of human perception relies on simultaneously understanding geometry, semantics, and relations in 3D. Indeed, what happens is that if you look at, if you try to run current algorithms, neural network-based algorithms for 2D semantic segmentation, which are working in 2D, they will still fail to interpret this image. They will detect a person, and they will fail to realize that the person is painted actually on the van. So essentially, the question we ask is, to go beyond existing algorithms, can we develop algorithms and systems that allow our robots to understand 3D scenes, including geometry, semantics, and relations? So our first results in this direction was the development of a library, which is called Chimera, that allows to map an unknown environment and understand the presence and semantics of different objects in the environment. So let me play the video here. Chimera takes standard images as input as well as inertial data. And in real time, it creates a 3D mesh model of the environment. So what you see in the video is not a 2D video, it's just the rendering of 3D model. And you will see also a top view of the model on the right. So the 3D mesh, of course, describes the geometry of the environment, but also each phase of the mesh is color-coded depending on which type of object the phase belongs to. For example, gray corresponds to the ground, green corresponds to the chair, yellow will be the cubicles, and so on. So in other words, Chimera allows our robots to reason in 3D and simultaneously understand the geometry of the obstacles in the scene, as well as which type of obstacles it observes. By the way, Chimera is open source, and if you're curious, you can check it out on GitHub. Moving beyond Chimera, we have also thought about how to capture relations, how to model relation between objects, and also have our robots understand high-level concepts such as rooms and buildings. So what I'm showing here is more for indoor environments and for robotics, but the same ideas can be applied outdoors for autonomous vehicles. So what we are doing essentially is to develop Hydra, which is an example of spatial perception system, which builds at the same time a high-level model of the environment in real time. So the example that you see in the video refers to an indoor environment, and Hydra, as you can see, is able to build a map of the environment, localize the robot as it moves through the environment, which is the magenta line, localize objects, understands the presence of rooms, buildings, and so on. Okay, so this representation is what is called a 3D scene graph, which is also a popular representation in computer graphics to simulate complex scenes. In a sense, what we are doing here, and let me pause the video because it's distracting just for a second. What we are doing here is some sort of inverse graphics, since from a sequence of images, we're reconstructing a virtual model or a digital twin, if you want, of the environment. Something that is not very dissimilar from a high definition map of the environment that we are used to in self-driving. But remember that what we do here is built in real time and without human supervision. So we have tested Hydra in a number of simulated and real environments that I'm showing here in the video. And we have shown, again, real-time construction of a scene graph for indoor environments. This is an example taken from a student residence at MIT. And again, you can see the construction of the scene graph, including the segmentation of objects, rooms, building, including a side view and a top view. And currently, we are in the process of stress testing Hydra, this spatial perception system, on several robotics platforms, including drones, wheeled robots, as the one that you see over here, and quadrupeds. besides proposing these real-time spatial perception systems, we have also developed new learning architectures called neural trees, which allow to infer the label of some of the nodes in the scene graph. For instance, this architecture allows inferring which type of room the robot is moving across by looking at the type of objects observed in that room. Okay, since I'm running out of time here, let me move to the last, briefly, to the last part of this presentation, where I want to go back to self-driving and discuss how to develop monitoring tools to detect failures of perception systems. So modern perception systems on self-driving vehicles run several algorithms in parallel and perform a multitude of tasks. As I mentioned earlier in the presentation, the perception system will need to build a map of the traversable space, will detect and track other vehicles and pedestrians, detect traffic lights and traffic signs. And we have already noticed that a failure in any of these capabilities might lead to dire consequences. For example, may lead to misdetecting a pedestrian or misunderstanding where the lane is. Therefore, in the last few years, we started asking questions such as, can we detect if some modules in a perception system are producing incorrect results? And this has led to the development of monitoring tools to detect failures at runtime. We also started investigating if, for a given architecture, we can quantify the number of faults that can be correctly detected. In other words, we investigated whether we can measure the resilience of a given perception system. So for today, I will not touch on the second question, but I will just give you a brief overview of the monitoring tools we developed for perception. So while this research line is still in progress, I just want to give you some intuition about the approaches we are looking into. So imagine that, again, you have a self-driving car, which is running a number of algorithms as part of its onboard perception system. For instance, the car will have some onboard sensors, such as a LiDAR, cameras, and so on. It will have maybe a module performing lane detection. Then we'll have some module performing object detection using cameras, maybe a LiDAR-based object detector. And then, the intuition behind the approach, the monitoring approach we design, is that we can essentially check if the detection from some of these modules are consistent with each other. For instance, we can check if the detected cars belong to the lane. We can check if the camera and LiDAR detections are consistent with each other. We can check the geometry of the lane. We can check that the geometry of the lane is consistent with the sensor data. In other words, we expect the lane to be flat, and the returns from the LiDAR should picture a flat plane for the lane, and so on and so forth. In other words, we can reason over inconsistencies between the output of different perception algorithms to detect failures. So we formalize these consistency checks by using an idea or a model which is called diagnostic graphs, which is a framework popularized for fault detection in multiprocessor systems a while ago, which we now adapt to perception systems. You can think about each node in the diagnostic graph to be a module in our perception system, and the module can be either faulty or fault-free. And then we can perform checks for each edge in this graph. So for each edge, we can essentially check the compatibility between the outputs of these modules. So the problem then becomes, given the test results corresponding to the edges in this graph, can we figure out what is the most likely set of faults producing these test results? And so we have investigated algorithms to perform inference over diagnostic graphs, including deterministic algorithms that use graph theory and integer programming to infer the set of faults, probabilistic inference, which are converting the diagnostic graph into a factor graph into probabilistic inference, as well as learning-based approaches, which are using graph neural networks to infer, essentially to learn how to detect faults. Just as a final video before I conclude, so to showcase our monitoring tool, we essentially recreated some of the recent self-driving car accidents in a realistic simulator. And we have tried to apply our monitoring tool to a state-of-the-art open source perception stack, which is called Apollo Auto. Many of you might be familiar with this. So in this example in the video is based on a Tesla accident dating back, going back to 2020. And what you see here on the left is a top view of the map where we annotate the map with the fault detection results. So green is going to be no fault, orange is going to be detection of low severity faults, and red is going to be high severity fault. So you can see here that as the car drives, the camera sometimes fails to detect, is misdetecting the vehicle on the opposite lane. And our monitoring tool, monitoring framework, is able to detect that inconsistency and report a low severity fault, as the one that you see here at the top left. However, at some point in the simulator, the car is facing an overturned truck, which you see here, over here. And the truck is not recognized by the camera, but is recognized by the LiDAR. Therefore, by looking at this inconsistency, our monitoring framework is able to understand that there is a failure and is able to stop the car before the accident occurs. Okay, so let me conclude here. In this short presentation, as a summary, I started from some basic facts about the promising reality of automated driving. Then I zoomed in on key algorithmic capabilities for autonomous driving, which are spatial perception. And then I discussed some of our efforts targeting spatial perception for robotics and autonomous vehicles. In particular, I touched on the work on certifiable perception algorithms that aim at designing estimation techniques which are robust to large noise and outliers. I mentioned the fact that robust autonomy requires high-level 3D scene understanding, and I introduced two libraries, Chimera and Hydra, which are able to perform real-time scene understanding on a robot. And then I concluded with recent work on fault detection in perception systems. So as a concluding thought here, I just want to remark that the way to level 5 automated driving is still a long one, and requires really a close collaboration. Requires a close collaboration between companies, governments, and academia, since it really involves a number of just challenging technical problems. At the bottom of the slide, I just want to show a summary of the 5 areas of safety in driving, in self-driving, which one can find on the NHTSA website. And I find this timeline quite instructive. So the timeline is showing the progress from early safety features such as seatbelts and cruise control developed between the 50s and the year 2000, the introduction of advanced safety features such as the ESC in early 2000, to more recent technologies, including automatic emergency braking and lane keeping. This plot is just a way to say that while the road to fully automated driving might be long, there are also many opportunities along such a way, and the push towards level 5, towards fully autonomous driving, will have also the desirable effect of giving us novel safety features in the short term. This being said, I will finish here, and I look forward to discussing with all of you.
Great, thank you so much. Look at this. This is such a rich set of material here. So I'll start with some question. Maybe start with the more technology side and gradually moving into the business and industry and the society side, right? So the technology side, I'll start with the sensors, right? So as a human being, we perceive the world with multimodal sensors. We see, we hear, we touch, we smell. And in the autonomous car, it seems there's the debate of should we use a LiDAR, should we use a camera, should we combine them? So what do you see as this potential of the trade-off or some potential combination of a multiple set of technology on sensors?
It's a great question. So maybe let me start by saying what are the most popular, the most common sensors that one would use for a self-driving car. Definitely cameras. Cameras are providing rich information about the environment. They're quite cheap, so that is it's really just a no-brainer to use them. Typically, on top of cameras, one is using distance sensors such as LiDARs, ultrasonic sensors, radar, and then there are other sensors which are more measuring. These are called proprioceptive sensors, which are measuring some quantity or property of the car. For example, you would use accelerometers, maybe inertial sensors, just to understand how the car is moving and so on. And of course, there's been a lot of debate about sensors. Like Elon Musk at some point said that self-driving car companies using LiDARs are doomed to fail. My personal take as somebody working from the technology standpoint, using this sensor data to build a model of the external world, my point is that each of these sensors are providing really complementary and different features. Cameras, again, are indispensable, are really fundamental just to give information about appearance, maybe detection of stop signs and so on. And again, they're quite cheap sensors, but at the same time, they provide rich sensor data, which is quite difficult to interpret. It's taken more than 70 years of computer vision maybe a little bit less, but many, many decades of computer vision just to get to the state of the art that we are seeing right now. So vision is definitely a tough problem, and it's definitely risky just to trust the detection from a neural network alone for self-driving. LiDAR has been just a sensor of choice because it's an amazing sensor. It's providing very accurate distance measurements, and it makes it immediate to detect an obstacle, right? As the case of the overturned truck I was doing in simulation, the LiDAR will be just nice. Even without understanding which object it's looking at, will just detect an obstacle. It will allow the car to stop. At the same time, LiDARs are quite expensive sensors. And traditional LiDARs will have moving parts, meaning that there is some mirror that will rotate inside the LiDAR to look around the car for distances around the car. And while of course there is ongoing work in research and industry about solid state LiDARs, these sensors are quite expensive, are in the order of hundreds to thousands of dollars versus a camera that can be just $1 for an iPhone camera, right? Then in this picture, there are also other sensors such as radar. Radar will have a much longer range than LiDARs and so on. It will also detect objects, will not worry too much about weather conditions, right? We detect objects through rain, fog, snow, and so on. And we'll also be able to measure velocities of the object it is looking at. So my take is that, of course, because of the complementarity of these sensors, in a sense, the more the better, right? So the more sensors you have, the more information you have to create redundancy in your system and make sure that your system is correctly understanding reality.
Thanks. Yeah.
So just as a final conclusion, I think that the question really is not about, do you want more sensors or not? The question is about the trade-off that you want to have. What is the trade-off between safety and cost that you want to pick? And of course, when Elon Musk is suggesting some trade-off, is also having in mind considerations which are non-technical. At the same time, there is this idea that is often made, which if humans are able to understand the world with two eyes, we don't need LiDAR, which I think is kind of a logic fallacy in the sense that current algorithms that you use for self-driving cars are not as powerful as the human brain, and current cameras are not as powerful and do not have the dynamic range of the human eyes. So we have to be careful about drawing conclusions about what can be done right now.
Thank you. Yeah. So the next one is after the sensor collect the data, what's the analytical model and the framework, right? It seems that in almost many transportation field, there's this constant tension between the learning-based model that really getting popular versus more classic theory-based model. It seems that the similar tension also exists in this computer perception side. I'd like to see your comments on this, but I want to also broaden the question to the fact that when humans perceive the object, etc., not only we have the sensor, but we have a huge set of common sense as the background here, right? We connect the sensor with our judgment. We have this intuitive physics, intuitive psychology, based on which we digest this sensor data. That relates to your work on the 3D understanding rather than just perceive, but you have to understand, right? So what do you see as the current state in terms of both the learning model versus classical model, but also how do we incorporate this common sense and intuitive physics in this process?
Yeah, so just to provide some comments, some context from the question, you have to understand that the community, both the robotics and computer vision community, were taken by storm in around 2012 maybe, because most of the community was working on traditional techniques, doing model-based optimization and thinking about geometry and so on. Then starting from 2012, there was a huge explosion in neural networks and deep learning, which is actually a pretty old technique, but thanks to the amount of data that was available and to the new computers, started working essentially very, very well. So there is really kind of a tension between these two techniques. However, I think as a field, we're starting to realize more and more, there is a clear trade-off between these two. The pros and cons of learning-based versus traditional methods is starting to become more and more clearer and clearer, if you want. So for learning, for example, you have the downside of needing plenty of training data sets, right? You need a human typically to annotate a lot of training data, which can be expensive, time-consuming, and so on. And the learning method typically will not work in the best possible way if you're testing something that is far from the training data set. So you have to be careful about the training data set being representative of the actual operating conditions of the car. And moreover, these learning-based methods are running on powerful GPUs. So there are also power considerations to be made. On the other hand, model-based approaches are still able to achieve state-of-the-art in many tasks about geometric understanding, pose estimation, SLAM. These are often still dominated by geometric traditional methods, if you want. And the advantage of those is that essentially you don't require training data. Geometry will be the same anywhere you go. So you don't require training data. The approaches will just generalize independently on the setup that you test. But at the same time, these traditional methods will always have some parameter that you need to tune, and will still typically process the output of some neural network eventually, as I was showing in my slides. So once you understand that there are the pros and cons of learning-based method and traditional methods, I think, again, also the robotics community is coming to the realization that rather than jumping in, rather than forgetting traditional methods and just adopting neural networks, there is just an opportunity to get the best of both worlds. And the opportunity, of course, different researchers will give you different feedback about this. But I believe the opportunity is really to connect learning-based modules, neural networks, and traditional approaches, and try to have traditional approaches essentially self-supervised, maybe the learning-based approaches. And this has been triggered by recent work on differentiable optimization, in which you can have model-based approaches, but you can differentiate through them, and you can include them as part of the training of a neural network. So in other words, if you have an architecture in which you can combine both approaches at the same time and train these architectures simultaneously, in one shot, recent results are showing that seems to be a quite promising way, which has the potential to reduce the amount of training data that you need and also give better performance. Very long answer.
Right, thanks. Last question I'll pose together, and then I'll pass to the audience. Please continue to add question remarks to that. So it's you described so far is the certifiable perception as an algorithm, right? So that's a mathematical property question here, right? So from that to get to the certifiable vehicle or certifiable mobility system, right? That's like a bigger jump in that. I like to see how the industry is evolving in this thinking. And also another thing is since 2018, you mentioned the accident to now, this 3 or 4 years passed. How much progress have we made, right? So in industry as a whole, are we making incremental progress, or are we making some major changes? Are we reaching a plateau? What's your assessment of the whole status quo of the industry?
Yeah, so let me start from the certification question. I get that question a lot. I think it's a fascinating question. It's a very nice one. And maybe just to give some context, there is a question about why certification, the way you mean it, is about finding a protocol to guarantee that, to evaluate a self-driving car and guarantee that it's safe. So it's a procedure rather than algorithmic property, as the one that I was discussing in the slide, is really about a protocol that you follow to certify a vehicle. So maybe I can break down the question into aspects. I can tell you why certification is challenging for self-driving, and then I can tell you what are the current practice. It's not going to be a perfect answer I'm going to give, but maybe will be helpful. So why certification challenging? I'm coming from aerospace, and aerospace, of course, has plenty of well-established certification approaches. So for if you want to fly or to sell an airplane, essentially you have to get an airworthiness certificate, which is telling that the airplane flies safely. And there is a standard procedure to do that. You have a design review, you have somebody testing the different modules and the airplane on the ground, and then you will have some test pilot testing different operating conditions in the air. And you have to you have to consider that in aerospace, this is a process which is going to take years, right? So to certify the safety of an airplane. So why this does not apply to self-driving? I think the main challenge there, or one of the main challenges, is that self-driving is heavily relying on sensors such as cameras or LiDAR, for which characterizing the operational domain is very tricky. While I can say the airplane is going to fly at this altitude is going to must safely fly, like, you know, within this temperature range, within this speed. How do we really characterize the different conditions that a LiDAR or a camera can face, right? You have to start talking about different weather conditions. You have to start talking about the angle at which the sun is impacting the camera. It's very difficult to describe as a design domain, as an operational domain. And of course, when you start using learning-based components in which safety is also a result of the training data set that you use, the problem is just extremely challenging to solve. On top of that, you have to think that while airplanes are operated by expert pilots, we expect self-driving cars to be operated maybe by nobody or by common users. And just to make the problem even more complicated, in aerospace, again, you can wait for years. You will have these big projects designing new airplanes, and you can wait for years to be certified. It's unclear how can we scale this up to a self-driving car in which you want to have monthly updates of the software. Is really unclear. So while I don't think there is really a standard way to certification at this point, I can tell you that there are standard metrics that one looks at in order to claim safety of an autonomous vehicle. One thing's typical about miles without collision, number of miles driven. And of course, like, you know, each of these metrics will have some shortcoming. For example, miles are different. If you consider miles driven in a challenging, cluttered urban environment, they're quite different from the miles you drive on a highway. Besides miles driven without collision, there is simulation, but simulation, also testing in simulation, is just as good as how the simulation is pictured in reality. So it's not a great metric, it's not a very reliable metric. Then there is scenario-based testing. Scenario-based testing, essentially, you create a number of corner cases and you see how the car is doing in these corner cases. This, I would argue, is typically the way we get driver licenses as humans. We test just corner cases. But of course, if you have to start considering all potential corner cases a perception system can face, is really like an extensive list. It's very tough to get this list of corner cases. And people are also claiming safety by measuring the number of disengagement, the number of time the user has to take over the system. But again, it's tough to use that as a safety measure. Like, you know, it's indicative of how well the system is doing, but it's only correlated, I think, to safety rather than being a perfect measure. Maybe a couple of things that I want to mention, and then I will stop here to make sure that we have time. There are also a couple of standards. There is the ISO standard, I think it's called 21448, which is starting to think about how to discuss safety, but they are very early stages. They are not prescribing some requirements. They are just informing stakeholders about potential risks and things to be careful about.
Thank you, Luca. Annie?
Thanks so much, Jinhua and Luca. This is fascinating. We have an active chat, as I'm sure you've seen popping up on the side here. I want to start with a kind of simple initial question, which is SM, they put their name in, mentioned that for the crash into the divider that you cited, couldn't a navigation map, using that as an additional input, have solved that problem, that it wouldn't have gone into the Jersey barrier there? And Dingpeng Wang was also mentioning what role will asking what role will an HD map play in an autonomous car, and so what I guess additional inputs might be able to supplement this other information that you're collecting?
Yeah, and by the way, I remember that I realized that I also answered just the first question from Jinhua, but let's move on and maybe we'll go back to the recent progress over the last few years. So HD maps are important, right? If you look at the strategy for most self-driving car companies, they are heavily relying on HD maps. There's some prior information about the geometry of the environment, as well as information about annotations, right? Where are the stop signs? Where are the traffic lights? So an updated HD map would have been very useful. Maybe that's my guess, of course, like, you know, without having like, you know, inside knowledge about the problem, I can share that an HD map would have helped in preventing an accident if the separator was not was present in the HD map. At the same time, I believe that that example of accidents is exemplifying a more general problem, right? HD maps are not instantaneous maps, are maps that are built at some point in time and they are used later in time. So they will not capture very recent road constructions. They will not capture very recent things. And that's why I think there can be a support for navigation but we also need to rely on very advanced, as I was saying, mapping or spatial perception systems, which are giving a real-time understanding of the scene on top of the prior information that we have from the HD map. And just to conclude, I think HD map, the other issue is that, again, they're fundamental right now, but they're very expensive and time-consuming to build. So having like a solution for spatial perception that is so powerful that can get rid of HD maps would be a huge economic opportunity for self-driving.
That actually, I was going to jump to a different set, but there's a chat or a conversation in the chat about how long until the demand for LiDAR creates enough economies of scale to actually bring the price of LiDAR down too. Do you have any speculation on that?
Yeah, I think that will happen. That will happen, and you will see this kind of promises also from the main manufacturers, LiDAR manufacturers. For example, I don't know, in the early days in which Waymo was starting to put this big LiDAR on top of their cars, the cost of that LiDAR was in the order of, I don't know, $70,000, was something like, really substantial considering the cost of the car. And now if you look at, for example, recent releases of solid state LiDARs, for example, from Velodyne, I was reading an article about this on the Velodyne website, which is one of the biggest producers of LiDAR. You can see that they're starting to promise cheap solutions. I think they're talking about solid state LiDAR being available at $500 up, once the scaling is there. So that trend is going to be there for sure. And I think LiDAR, for most of the self-driving car companies, will still play a role in the short term. Eventually, I may agree with Elon Musk. After we solve computer vision completely, we can get rid of the LiDAR, but I don't see that happening in the very short term.
And I did want to give credit. That was David Chant that asked that question. Then we also have a couple of questions about, let's say, bad actors. Saeed Saidi was wondering about the cybersecurity risks of AVs more generally and kind of the what you're proposing here. And Sal Tannenbaum was also saying, are these algorithms tested against adversarial inputs from the start? Or is the assumption that the inputs will always be friendly?
Yeah. Is this referring to the certifiable perception algorithms, or is it a more general question?
I think it's a more general question.
Yeah, I think that's that's still a problem. I'm not an expert in cybersecurity, but I can tell you that, for example, in terms of adversarial inputs, there is part of the community in Vision, which is again trying to build these adversarial examples, understand how to make networks robust to these adversarial examples. But the current reality is that it's quite easy to build adversarial examples that can force a neural network to be confused, not to detect a stop sign, as I was showing in the slide, or just to fail to understand the world around them. And I think this goes back to Jinhua's point. These neural networks are still lacking common sense. So in a sense, the fact that they're easy to attack is a consequence of the fact that the network is not able to reason in a holistic manner about the scene, but is just doing very greedy understanding of the objects and so on. So I think that's a problem. And you can find plenty of examples online about people drawing maybe a circular lane around the car and just trapping the self-driving car inside the lane. Or there is a lot you can do to confuse the cars. Not to talk about attacks on the specific sensors. You can flash a beam of light into a LiDAR and create artifacts in the LiDAR measurements. Yeah, so these are all risks.